In this section, we're going to be talking about exponential growth and decay problems, and then we're also going to just briefly touch on Newton's law of cooling. So, what's so wonderful about now that you've learned about the exponentials and then the logarithms is that just opens up a whole new world to you. You know, if you're going to do anything in chemistry or the biological sciences at all, then you absolutely see these formulas because we know these most commonly as growth and decay formulas. Now, if you're looking in several different textbooks, several different textbooks present things so many different ways, and as if they are something different. You'll see things like, A equals A naught e to the kt. You may also see it written in absolute function notation. So A in terms of t equals A naught e to the kt, and then they'll say k is less than 0. Or here they're using ends and saying k is greater than 0. But looking at each one of those formulas, don't they all look remarkably the same? You've got something here, and then e to the kt on every single one of them. Let's just take it down to what it is. These are all really the same formula. If you can just remember one, that's so much better. The only difference here really in these is this first number, and then they say k greater than 0 or less than 0. Well, let's just kind of ignore that for a second. Let's just look at A equals A naught e to the kt. Let's look at what each one of these parts are. Your A naught, or your A sub 0, anytime you see this sub 0, that almost always means an initial or a starting amount. So you see how we have for our A naught is our starting or our initial amount. Sorry about that. The plain A here is our amount after time. So no matter whether we use A's or N's or function notation, this is still a starting value, or a starting amount of items, and an ending amount. That's what those positions represent. Now, t is your time, of course. We have our t here, and that can be in any increments at all. I mean, if we're talking about days, then we assume it to be days. If we're talking about minutes, we assume it to be minutes. It can take on any different time frame that it wants to. Finally, here we have this k. K in this formula represents what's called the proportionality constant. And the proportionality constant is really actually what's the most important thing. And you'll notice that up in these different variations here, they said we have k greater than 0 in this type of problem and k less than 0 in this type. They're all the exact same thing. It just depends on whether k is positive or negative. So you can make you a little note here. If k is positive or greater than 0, then we call this a growth function or formula. If k is less than 0, then we call this a decay function or formula because our exponential is going to be going down. Okay, we're going to work some problems and use this, but I also, before we end this video, which I only have about a minute left, I also want to go over another formula here, which is Newton's law of cooling. And Newton's law of cooling follows this formula. Now again, you have to know what all the pieces are, and that makes things so much easier. Just like we talked about before, this mu naught or mu sub 0 is our initial or our starting amount. And we're talking about things cooling off, so temperature. So you see how they have mu naught is your initial or starting temperature. And then your mu here is their temperature after time. Very similar to the A and the A naught earlier. The capital T's here represent our constant or our ambient temperature. This is the temperature of the room or the medium that you're going into when things are cooling down. K again is our proportionality constant, and T is our time. And again, it can be in minutes or hours or whatever we're working with. Generally, when we work with cooling problems, we're talking about minutes.